Hi everyone, I hope you're doing well. I'm making a series of videos for you on 7.2 dot product since we couldn't have our live lesson on Friday. So I want to start with just recapping the operations with vectors that we've talked about so far, or that you've learned about so far. So one of them is addition, another one subtraction, and then scalar multiplication. And just recall that scalar multiplication is multiplying a scalar by a vector, which will change its magnitude, can either make it larger magnitude or smaller, depending on what type of scalar it is, if it's a whole number or a fraction that you're multiplying by. Can also turn it around in the opposite direction if the scalar is negative, or make it into the zero vector if the scalar that you're multiplying by is zero. So the next operation that we need to look at is vector times vector. Does it actually exist, and if so, what is the meaning of it and how does it work? So it turns out this operation is actually called the dot product, and sometimes called the scalar product. You'll see why soon. And so what I want to show you here with this applet is what the dot product of vectors actually means. So this, just ignore the denominator here, which has the magnitude of b for a minute, and we're looking at a dot b here. Vector a dot vector b, if we take vector a and put it exactly on top of vector b, could be shorter or longer, doesn't really matter. Oops, I've changed b. Let me change a here. Okay, so I'm going to make a shorter. So what we're looking at, just look at the numbers, how they change. So from here, I got closer to b, and now I'm making a's magnitude closer to the magnitude of b. And what you'll notice about the dot product is that the number gets bigger, the value of the dot product gets bigger. So the dot product of a and b is actually, one way of thinking of it is the directional growth of b, meaning how much of vector b is in the direction, how much of vector a is in the direction of vector b. So that as the direction and magnitude of vector a get closer to that of vector b, the dot product of the two gets larger. Now what would happen if these two vectors were perpendicular? So I'm gonna, I'm just playing with this applet but not playing with it properly right now. I'm going to take vector a back here until it is approximately 90 degrees with vector b. So the angle between them is in radians, which means that in order for it to be 90 degrees, the angle between them would have to be pi over 2, which is approximately 1.57 radians. So I've done it. I've made it exactly 1.57 radians, which would be pi over 2, a 90-degree angle between a and b. And what do we notice about the dot product between a and b? It's equal to 0. Now let's take a in the opposite direction of b. And so we're actually taking away from the directional growth of vector b. We're not making it longer or stronger. We're making it weaker because vector a is going in the opposite direction. And what do we notice about the dot product of a and b? It's negative. So that's telling us that vector b is becoming weaker because vector a is in the opposite direction to it, or a negative direction from it. Okay, so that, I felt like this was a really good way to understand the abstract meaning of dot product. So let me go over to the whiteboard now. And over here I've just written a couple things about the vector operations we've looked at so far. Scalar multiplication is known as scalar times a vector, and vector times vector we just found out is called the dot or scalar product. So let's get down a definition for dot product. There are actually two. There's a definition for dot product when we consider geometric vectors, which is from chapter 6, and then there's another one if we consider the vectors as Cartesian vectors. So starting with, for geometric vectors a and b, then the dot product will be defined to be the magnitude of vector A times the magnitude of vector B times the cosine of theta, where theta is the angle between vectors A and B when they are positioned tail to tail. So theta is angle between A and B. So this is different than adding the vectors when they go tip to tail. When tail to tail. And you'll see what that looks like in a minute in example 2, which I'm going to do now. So I'm looking at example 2 on page 371 in your textbook. And part A gives us two vectors that are positioned tail to tail, vector B and vector A, with an angle of 40 degrees between them. And we're given their magnitudes. So the magnitude of B is given as 30 units, whatever units we don't know, but we'll just call it units. And vector A has magnitude of 20 units. So according to our definition for geometric vectors that I just wrote down, to find the dot product of these two vectors, let me just go to the next page here. A dot B would be equal to the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. Magnitude of vector A was given as 20, magnitude of vector B is 30, angle between them is 40 degrees. And so if we just calculate that with our calculators, make sure your calculator is now in degree mode because the angle given is in degrees. Comes out to approximately 459.6. So what does this tell us about vectors A and B? Well, we know how vectors A and B relate to each other because we were given the diagram. But if we didn't, it would tell, since the dot product of the two vectors is positive, it would tell us that vector A and B are more in the same direction than they are in different directions, because the directional growth of one of them is being made much stronger by the other, which the magnitude of this dot product is much larger than the magnitude of each of the vectors. Now, note that the dot product of the two vectors is a scalar quantity, not a vector quantity. And that's the reason why the dot product is sometimes called the scalar product of two vectors. So I'm going to talk about that a little bit more in a bit. Let's just look at example 2, part B now. And as you can see in part B, the vectors are perpendicular to each other. And so based on what I showed you in the applet a minute ago, if you remember, what should the dot product of the two vectors be? I'll let you think about that for a minute. And let's actually do it with the formula and see if it agrees with the prediction that you have in your mind. So m dot n should be the magnitude of vector m times the magnitude, of vector n, cosine of 90 degrees, which is 60 times 75 cos 90. And if you remember off the top of your head, cos 90 is 0. If you don't, just do it in your calculator. And so the dot product of the two vectors comes to 0, which is what we saw in the applet, that when the vectors are perpendicular, then the dot product of those two vectors will be 0. All right. Now looking at part C of this question, what would we expect the dot product to come out as, positive, 0, or negative? If you look at the two vectors u and v, they are more than 90 degrees apart from each other when positioned tail to tail. And then if you look at the solution to part C, the dot product is in fact negative because since they're more than 90 degrees apart, one of them is diminishing the directional growth of the other to some extent. All right, let's move on to the definition of dot product for Cartesian vectors. So if we're given two vectors A and B, written as Cartesian vectors, and so we can write vector A as A1, A2, those are the components of vector A, and vector B as B1, B2, then the definition of dot product here, A dot B, would be equal to A1, B1, so the first component of vector A times first component of vector B, plus A2, B2. All right, let's have a look at question number 4 on page 376 to see how that works. So page 376 in your textbook, question number 4a we'll start with. Calculate dot product of each pair of vectors. So we're given vector u equals 2, 4. Vector v equals 3, negative 1. So we don't know what angle is between them at this point because they're given as component vectors. Let's go ahead and find the dot product and see if that gives us any information about the angle between the two vectors. So we need to do first component of first component of u times first component of v, which would be 2 times 3, plus second component of u times second component of v, which is 4 times negative 1. So that's 6 minus 4, which is positive 2. Note again that the answer is a scalar quantity. And so what does the fact that this scalar product is positive tell us about the angle between the two vectors? It tells us the angle between them is less than 90 degrees. And so one of the vectors is increasing the directional growth of the other vector in terms of an analogy that we looked at before. For part B, we're given vector m equal to negative 5, negative 7, and vector n 0, 7. And so m dot n would be negative 5 times 0, which is 0, plus negative 7 times 7, which is negative 49. And so the result is negative 49. And what does that tell us about vectors u and v? It tells us that the directional growth is being diminished by one vector from the other, and that the angle between them is greater than 90 degrees. And let's look at one more question here, 4e. Oops. 4e, we're given vector A is equal to 2i plus 3j. Remember that I like to write unit vectors with this little hat on top instead of a vector symbol, just to make it obvious that it's a unit, that they're unit vectors and not regular vectors. Vector B equals 9i minus 7j. And so this is the unit vector notation of vectors, which you should have seen in the gizmo, the Explore Learning gizmo that you did for 7.1. We can rewrite these vectors in component form if we want. We don't have to. We could do the dot product directly from here, but We could also rewrite vector A in component form as 2, 3, for example, and vector B in component form as 9, negative 7. And then we can go ahead and do the dot product from there, which would be 2 times 9 plus 3 times negative 7. And so that's 18 minus 21 equals negative 3. Now I meant to tell you, I just want to go back here to the definition of dot product for a minute, definitions of dot product. So this one here, that if you wish to work through the proof on page 373 in your textbook, it's quite well done. And so if that can be an extension activity for you if you're interested. If you are going to be taking linear algebra next year or focusing on math, then it's a really good idea to work through that. It will help you for next year. But that's up to you if you would like to do so. And I'm going to make a couple more videos for you. So I'm going to end this one here for now and see you soon.